Many protocols and algorithms require the serialization or enumeration of related entities. For example, a communication protocol must know whether some packet comes before or after some other packet. The entities.For RFC 1982 attempts to define serial number arithmetic for the purposes of manipulating and comparing these sequence numbers. This task is rather more complex than it might first appear, because most algorithms use fixed-size representations for sequence numbers. It is often important for the algorithm not to break down when the numbers become so large that they are incremented one last time in wrap around their maximum numeric ranges. Unfortunately, some protocols choose to ignore these issues, and simply use very large integers for their counters, in the hope that the program will be replaced before the problem occurs. Many communication protocols apply serial number arithmetic to packet sequence numbers in their implementation of a sliding window protocol. Some versions of TCP use protection against wrapped sequence numbers. PAWS applies the same serial number arithmetic to packet timestamps, using the timestamp as an extension of the high-order bit of the sequence number. Operations on sequence numbers. Only addition of a small positive integer to a sequence number, and comparison of two sequence numbers are discussed. Only unsigned binary implementations are discussed, with an arbitrary size in bits noted throughout the RFC as serial_bits. Addition. Adding an integer to a sequence number is simple unsigned integer addition, followed by unsigned modulo operation to bring the result back into range. S equals modulo addition of a value outside the range. 0, 1 is undefined. Basically, adding values beyond this range will cause the resultant sequence number to wrap and result in a number that is considered less than the original sequence number. Comparison. A means of comparing two sequence numbers I1 and I2 is presented. Equality is defined as simple numeric equality. The algorithm presented for comparison is very complex, having to take into account whether the first sequence number is close to the end of its range of values, and thus a smaller, wrapped number may actually be considered greater than the first sequence number. Thus S1 is considered less than S2, only if, or, likewise, S1 is considered greater than S2, only if, or, shortfalls. The algorithms presented by the RFC have at least one significant shortcoming. There are sequence numbers for which comparison is undefined. Since many algorithms are implemented independently by multiple, independent cooperating parties, it is often impossible to prevent all such situations from occurring. The authors of RFC 1982 simply punt, while it would be possible to define the test in such a way that the inequality would not have this surprising property. While being defined for all pairs of values, such a definition would be unnecessarily burdensome to implement, and difficult to understand, and would still allow cases where S1 less than S2 and greater than, which is just as non-intuitive. Thus the problem case is left undefined. Implementations are free to return either result, or to flag an error, and users must take care not to depend on any particular outcome. Usually this will mean avoiding allowing those particular pairs of numbers to coexist. Thus, it is often difficult or impossible to avoid all undefined comparisons of sequence numbers. However, a relatively simple solution is available. By mapping the unsigned sequence numbers onto signed twos complement arithmetic operations, every comparison of any sequence number is defined, and the comparison operation itself is dramatically simplified. All comparisons specified by the RFC retain their original truth values, only the formerly undefined comparisons are affected. General solution. The RFC 1982 algorithm specifies that, for n-bit sequence numbers, there are 2-1 values considered greater than, and 2-1 considered less than. Comparison against the remaining value is deemed to be undefined. Most modern hardware implements sign-to's complement binary arithmetic operations. These operations are fully defined for the entire range of values for any operands they are given, since any n-bit binary number can contain 2n distinct values. And since one of them is taken up by the value 0, there are an odd number of spots left for all the non-zero positive and negative numbers. There is simply one more negative number representable than there are positive. For example, a 16-bit 2's complement value may contain numbers ranging from -32,768 to +32,767. So, if we simply recast sequence numbers as 2's complement integers, and allow there to be one more sequence number considered less than there are sequence numbers considered greater than, we should be able to use simple signed arithmetic comparisons instead of the logically incomplete formulae proposed by the RFC. Here are some examples, comparing some random sequence numbers against the sequence number with the value 0. Unsigned binary signed sequence value distance 32,767 = 0 by 7 FFF = 32,767 1 = 0 x 0001 = 10 0 x 0000 0 65,535 = 0 x FFFF = -165,534 = 0 x FFFE = -232,768 = 0 by 8,000 = -32,768. It is easy to see that the signed interpretation of the sequence numbers are in the correct order, so long as we rotate the sequence number in question so that its 0 matches up with the sequence number we're comparing it against. It turns out that this is simply done using an unsigned subtraction, and simply interpreting the result as a sign-to's complement number. The result is the signed distance between the two sequence numbers. Once again, if I1 and I2 are the unsigned binary representations of the sequence numbers S1 and S2, the distance from S1 to S2 is distance equals. If distance is 0, the numbers are equal. If it is less than 0, then S1 is less than, or before, S2. Simple, clean and efficient, and fully defined. However, not without surprises. All sequence number arithmetic must deal with wrapping of sequence numbers. The number 2n-1 is equidistant in both directions. In RFC 1928 sequence number terms, in R math, they are both considered to be less than each other. Distance 1 = 0 by 8,000 equals -32,768 less than 0. Distance 2 = 0 by 8,000 equals -32,768 less than 0. This is obviously true for any two sequence numbers with distance of 0 by 8,000 between them. Furthermore, implementing serial number arithmetic using 2's complement arithmetic implies serial numbers of a bit length matching the machine's integer sizes, usually 16-bit, 32-bit and 64-bit. Implementing 20-bit serial numbers needs shifts. Distance equals, see the unit test cases in the example C++ implementation below for more examples.